So in this demo, we had 3 key components. We had locomotion, flight, and driving. When is the sum of the system greater than its parts? Historically, my lab has done a lot of work with model and physics-based methods for controlling robots. Things like walking and locomotion, purely using physics-based models to encode controllers. And the really important part about models is they're deterministic. You can get a certificate, and in particular, a proof, a mathematical proof, a theorem and a proof that your robot will do the right thing always. So how do we bring together different mobility types that robots have? So right now, robots can fly, robots can drive, and robots can walk. Those are all great in certain scenarios. But how do we take those different locomotion modalities and put them together into a single package so we can excel from all the benefits of these while mitigating the downfalls that each of them have? So the context is we want to get somewhere on Caltech. Let's say there is an emergency and we want to get there quickly with an autonomous agent. So how are we going to do that? Well, we have M4 and we have the humanoid. So the humanoid needs to carry M4 to a deployment zone. And the humanoid is very good at walking indoors and in buildings. So it first leaves Gates Thomas, walks through the library, gets to an elevated area, the launching pad on the other side of the library. And then at this point, we can now separate the team. And so the M4 takes off of the humanoid, switches to driving mode, and then starts to head towards its goal. Now, when it's driving there, it realizes there's a pond in the way. You can't drive over the pond, so you transform to flight mode and head over the pond in flight mode. So we had 2 M4s, we'll call them red M4 and white M4. The red one already existed, and that's what we had been sort of practicing on. The white one is the one that was built collaboratively with TII in the couple weeks that they were here. So it was a brand new M4. And that one has special things about it. For example, the compute that's happening is on something called the Saluki that TII developed from scratch themselves. So the Saluki is sitting on the M4, and the M4, of course, was designed at Caltech. So it really was a fusion of Caltech and TII together. At the same time, the humanoid ultimately wants to end up at the same location. It's a little bit slower outside than a flying drone, but it will walk there and it will get there eventually. So it needs to handle some things like it needs to walk around the long way, maybe take some stairs along the way. We had to realize a whole new form of locomotion on a humanoid robot that's never been realized before. If we want to really deploy robots in complicated scenarios, we need to be able to generate these actions without necessarily having human references. And instead of using human data, take these models and imbue the robots with the intelligence of the models, using modern machine learning methods coupled with the models and fuse them together, and then we learn to walk as the physics dictate. So these are the areas where a humanoid can really excel, handling terrain like that. But ultimately, it will get to that final location. They'll meet, and together they can solve the problem together. So the goal was to show all those pieces working in totality in the demo. When you have an idea of something new, and then you push it, not just in your lab, but push it in a demo way. So we push it outdoors into real-world environments and stress test it and see how well it works. And when it actually works, it's pretty amazing.